Okay, so yesterday, the main lesson of yesterday's lecture was the following, that to determine the low energy behavior of some system, the first point is to need to identify fixed points. And then what to need to do is to work close to the fixed point look at flows of the coupling, identify the relevant and irrelevant couplings, and then the space of relevant couplings determines the low energy behavior. And a prototypical pictorial way of understanding this, so what we saw is to have a picture like where this is some relevant coupling and this is some irrelevant coupling in this direction. And I pick a model. A model means a relationship between the couplings. And let me give you an example, since many of you asked you, is that if I start out, here is my model. Model is some constant A, not R. This is roughly like R grad phi whole square, but there will be terms which are just phi square in it, right? And so this in continuum would become, roughly speaking, R grad phi whole square plus phi square with some number here, with some other number here, which is grad square phi whole square, and so on. As we saw, these objects like grad phi whole square, grad square phi whole square, were in fact, and their related couplings, so let me call it couplings C, I think I call it C0, let me call it C2, and so on and so forth. So, and we found that these have the property that under a renormalization group transformation, Cn goes raised to the power 2n Cn, which means these are precisely the couplings which are either relevant or irrelevant. These are in fact those eigenvectors of the renormalization group. However, we started out with a model like this, and you might wonder, in order to do this process, if I have to write down a theory with infinite number of couplings, that doesn't sound very good. So in practical terms, what we want to understand is we are just starting with a specific lattice model which has just one parameter in it. Given just one parameter in it, can I describe the low energy physics? This is typically a problem in field theory, 1 or 2 or 3 parameters in it. And the point to note is that as I wrote it down, this is some equality here. So that means this C0, C2, C4 and C3 and so on, they are not independent of each other. They are all dependent on R. Their ratios are completely determined in this case. So there are non-trivial relationships between these couplings. Okay. So if I just take just two of those, what this means is C0 and C2 has a certain relationship with each other. So what I'll say is that this model determines a function, say C0 is some function of C2. There is a functional relationship between C0 and C2. In this particular case, it's just a proportionality with some number maybe. Okay. What this means is that in the space of C0 and C2, there is going to be a line. Each point of those line represents a different value of r, but all points on this line have the same relationship between C0 and C2. So this is the equation for the line is given by C0 as some function of C2. Okay. So then we argued that if I am to consider the low energy limit, or in other words what field theory is called a continuum limit of this theory, what I need to do is to take a sequence of theories on this line. That means in this language a sequence of this theory with different values of r, which successively come closer and closer and closer to this line C0 equal to 0. And as you come closer and closer, the RG flows sort of creep along this for a long time and eventually all sort of asymptote to this line. And since the correlation length on this entire line is infinite and the correlation length there is finite, therefore it must mean that I must assign a cutoff to each point. When I started out with this, r was a parameter. Different values of r were just different numbers. Now I have done something very non-trivial. This theory didn't know anything about units. There was no notion of a centimeter or electron volt or anything like that. Now by hand I have introduced a scale in the problem, a unit by which I am measuring everything, and I say different values of r correspond to different values of the cutoff. Okay. How do I know what value of the cutoff I should assign to each value of r? I know this by looking at how, by changing the value of r, how do I change the ultimate value of this relevant operator C0. So in other words, in this case things are extremely simple. Namely, if I write C0 as some physical mass square divided by the momentum space cutoff square, and in this case C0, let's say, I think in this case C0 is just 2 times phi square. So that means that for m physical to remain finite, I must have C0 go as 1 upon lambda square, which therefore means that the entire critical surface should correspond to a length scale where the momentum space cutoff has been taken to infinity, the position space cutoff has been taken to 0, and I can approximate the whole theory by a continuous field theory. The crucial point in our ability to do such a thing was the existence of a fixed point. If I don't have the fixed point, I don't have this behavior, and I cannot go ahead and have a meaningful construction of the theory. In the old days, now after you have done all that, then you realize that at low energies I can only talk about the relevant perturbations, but I can still ask that as I keep changing the scale, how does this relevant parameter changes? Okay. Each of these scales are represented by some physical length scale in the theory. This is not the original cutoff of the theory. Original cutoff is some lambda which has been taken to infinity, but I can still do an RG and start looking at, okay, I want to look at the physics at 10 GeV, I get one theory. Then I look at the physics at 5 GeV, I have another physics. And this flow at the same time tells you what is the relationship between the physics at 10 GeV, and the physics at 5 GeV, all of which is way below the cutoff of the theory, which I can take to the Planck mass. Planck mass has become irrelevant in this limit. Okay? This flow therefore tells you the relationship with this theory and the rate at which these couplings change, as we will define later as called these beta functions, essentially tell you the content of how to determine the low energy behavior from the theory at different values of the low energy. This language of talking about is called renormalized quantum field theory. In the old days, this is the way people used to talk about it in terms of the low energy scales being changed in the theory. Today I'll ask the question that how do I know that there are fixed points in a given theory? And in particular, I'll ask the following question and provide the answers which are given by these two particular models. The question I ask is as follows, and this is related to the last comment I made about critical phenomena. We noted in the simplest critical phenomena which is represented by a Landau theory with a scalar field which has the symmetry phi going to minus phi, there was one relevant operator. A typical Landau theory would have a Lagrangian which sort of looks like this. Phi 4. These are dimensional objects, but I can multiply by power of the cutoffs to get dimensional-less objects like r equal to r naught lambda square, u is equal to u to the power 4 minus d. And we noted that even though this theory had been successfully and brilliantly used in fact to Landau to obtain the first notions physics of critical phenomena, it obviously seems to be wrong in at least d equal to 3, because this operator phi to the 4, this coupling u doesn't seem to be a relevant operator. Sorry, this is d minus, yeah, sorry, this operator happens to be a relevant for d equal to 3 because the power of lambda is positive there. Okay. Whereas physics tells me it shouldn't be the case. In the simplest critical behavior, there should just one relevant operator, which we usually take to be a temperature. So this begs the question, this entire counting of dimensions and therefore the flows under the simple RG was based upon our intuition about free field theory on what we call the Gaussian fixed point. Okay? So I'm going to ask the following question. If I plot R0 and if I plot u, then as I noted yesterday, the flows of this various coupling, let me put u0 also, they sort of look like this. And then there was fixed point. And clearly, this fixed point cannot describe the low energy behavior of the physics I'm trying to understand. If a flow is going away from a fixed point, you got to ask the question, does it keep going on forever or does it stop somewhere? Okay, so there are just two alternatives. If the flow goes on forever, then your conclusion that that is a relevant perturbation and therefore at long distances that appears as a scale in the theory, just like a mass, is correct. If however this flow, for example, and as we will show, goes and ends somewhere, the conclusion is quite different. And the conclusion is different, again in coming back to that simple picture, is that whereas any point away from the critical surface sort of went off the critical surface eventually, a point exactly on the critical surface is going to the fixed point itself. Fixed point means it's just once it's there, it's just there. And we showed that the fixed point corresponds to a massless theory. It doesn't have any mass scale in there, it's just del phi whole square, right? I mean, that was a fixed point. So if this thing happens, then just by looking at these arrows, you can guess what the flow diagram would look like. I mean, there must be some continuity of these arrows, and suppose this one also goes like this. So therefore, a point here would flow like that, a point there instead of going all the way would flow like this, and so on. And then it is quite clear, regardless of where you are on this plane, unless you are exactly here, your low energy behavior is going to be governed not by this fixed point, by this other fixed point. Is this point clear? Just from the picture? Okay? Good. So I will now demonstrate. In this course, we will just demonstrate two examples of this kind of behavior. This kind of fixed point has a name which is called an infrared fixed point. It's called infrared because the flows are drawn in the direction as you go to longer and longer distances. The longer and longer distance and longer wavelengths are sufficient to probe those distances, and longer wavelength is going to the infrared. Okay. In a similar way, if I had a picture which is like that, coming to a fixed point, then you would say, oh, it's very happy. This one has just one relevant perturbation, so I know all the flows are sort of like that. However, you got to ask the question, does this come from infinity, or does it also start from another fixed point? Right? So if it did start from another fixed point, then things would be quite different. Right? Then the low energy behavior of any point which starts around here is going to govern by that fixed point, whereas from any point out here will be discussed by something which appears at large distances on this other side. Okay. So these are the two examples which I at least hope to get started on calculating in detail to see how such fixed points arise in this kind of theory. Okay? So let's start with this one. So before doing that, let me remind you some of the basic formula for calculating functional integrals. By and large, the only integral we know how to calculate is a Gaussian integral, and we want to basically reduce things to Gaussian integrals, and so I will give you those relationships for Gaussian integrals. Okay. So a typical example of a Gaussian integral is, this I already had discussed in some dimension. There is a half here, r phi square. That's a good Gaussian integral. I am ignoring all the other things, as you already noticed. I haven't written grad square phi whole square because it turns out there are other interesting fixed points which correspond to grad square phi whole square being held fixed, but I will not discuss those. Those are called Lifshitz fixed points. Yeah? Yeah? No. Okay? And then we wrote that in momentum space. I'll use a continuum notation. This is a Fourier transform of that field. So this integral just becomes symbolically and then I gave you an exact meaning of what is meant by this. In order to give an exact meaning of what is meant by this, you have to put the system in a box, you have to do a lattice, and then you have to then all these momenta are discrete, related in terms of discrete integers. Then it is just a multiple integral of phi's evaluated at the discrete points, except that you have to take into account the fact that original phi was a real field, so you have to cut it into half. But that's a question of detail. I want to do integrals like this. So how do I do such an integral? In fact, I'll make it a little more general by adding to this a term which is j phi. J is some arbitrary function of x. We will see this is very useful. Okay. So the basic formula for doing this is given by the multiple Gaussian integral formula. If you haven't done this ever, I suggest you just go home and do it, this integral. This is a Gaussian integral, and the result of this is some constant times a determinant of this matrix B raised to the power minus half. A quick way, actually, let me give you a quick way, since Shotto actually explained very well how to transform measures of integration, so might as well I do that. So I define a new variable by, this is an orthogonal matrix such that this matrix by a similarity transformation diagonalizes this matrix B. So psi I Bij psi j just becomes Bi square xi square. This is an orthogonal transformation. So the Jacobian of that orthogonal transformation is just 1. So I can go from variables from xi to the variables x. So this integral just becomes integral di dxi e to the minus Bi xi square, and you all know how to do this integral. I think there's probably no half here. It's just given by pi upon Bi with a product of I. The answer should be independent of what basis I use to write this matrix in the vector space, and this you immediately recognize is just root pi if there are n such indices n, and then determinant of b raised to the power minus half. That's where this formula comes from. Okay. A slight generalization of that formula, which we will need in evaluating this. So let me erase this. So this is given by that. Is the question of having and again by using that orthogonal transformation which diagonalizes this matrix, everything is real, so that's why orthogonal transformation diagonalizes this matrix. Then what you find is that the result of this integral is some irrelevant constant determinant b raised to the power minus 1, and then exponential of ji b inverse ij jj. This is also very easy to prove just by using the trick which I just showed up to evaluate the first integral. Okay. So what does this mean for this? In fact, I'm ignoring factors of 2, or an integral like this. This means that this integral is, now it is already in a form, once you break it up, the other day I showed how to break this up in terms of phi of k with k0 greater than 0 and less than 0. Once you are careful of that, the answer is it's a product over all k square plus r raised to the power minus half. That is the analog of determinant of b raised to the power minus half, and then an exponential of integral ddk prime t square plus r. This is the analog of this formula. Okay? Once again, if you haven't done this, it's not very difficult to do. You can just sit down and go ahead and do this. There's nothing fancy about it. So these are the only two formula which I will, yeah. Oh yeah, thank you. You didn't write ddk k prime, but it's already diagonal. Yeah, yeah. This is already diagonal. Right? The usefulness of doing this is that once I have this, I can calculate correlation functions. Because, so let me call this an object z of j. So if I take it is clear, so this is object is d phi e to the minus s plus integral j phi, as I just wrote, and then the derivative with respect to j brings down a minus sign, and phi at some point x, the division by j gives you this. So therefore, if I evaluate this at all the j of x equal to 0, I get the average value of phi of x in the original theory with j equal to 0. Similarly, if I take I get with a minus sign the two-point function at j equal to 0, and so on and so forth. Once you know this, you know how to calculate all the endpoint functions in the theory. Okay, I think that's all I will need to do the calculation. So let's start doing the calculation in this pretty non-trivial 5-4 theory. So this is what I'll do. So I'll calculate z, which is e to the minus s, and s in position space in momentum space. This becomes this is d, it's half u so this is clear. Clear to everybody? Good. All I've done is a Fourier transform of that. Now I'll do the first step of our RG transformation. So what was the first step of an RG transformation? Is that you separate out the field in terms of low momentum modes and high momentum modes, okay? And then you integrate out the high momentum modes. I have to provide the theory with a cutoff, so I'll use momentum space cutoff. What I mean is that this thing has k less than some lambda. Okay? And what I'll do is I'll write the field phi of k where phi L of k is given by phi of k for and 0 and phi s of k This was exactly as we did in the Gaussian theory. We broke up. I mean, there we were using units in units of the original cutoff. So we had our the original momenta lying between 0, 1, 1. We broke it up to 0 to 1 upon b and then 1 upon b to 1. Okay? That's exactly what I have done here. I have taken what I call phi L. L stands for long wavelengths, which have momenta which do not go all the way to the cutoff of the theory, which goes to somewhere below the cutoff of the theory, because b is always greater than 1. And these are the short wavelength modes which lie in this interval between lambda upon b and lambda. And then I will write the partition function in terms of, roughly speaking, d phi L of k, d phi s of k e to the minus s, and I'll integrate out d phi s of k, right. So I want to write this as d phi L of k times something called, which I'll call an effective action, and this serves as a definition of the effective action, namely e to the minus effective action is just given by the integral over the short wavelength modes times the original action. In the example I did, doing this integral was entirely trivial, because I only had this term basically. Basically things with two phi's. The thing with two phi's is that the phi, it comes as phi of k and phi of minus k, right. So the magnitude of k in each of these terms is the same, right. So this integral over k broke up into two pieces, the long wavelength piece plus the short wavelength piece, but no cross term in it, right. So then I can just go ahead and do the integral over the short wavelength pieces, but of course I cannot do that anymore because of the presence of this term, which mixes up everything. Okay. So this is the thing which will give you the non-trivial contributions to my renormalization group flow. So how do we calculate this? Okay. I want to keep that. Effective action of phi L, it is only a phi L because you have integrated out the phi s, is therefore given by the original action, and I'll call, so this part is S interaction, this part I'll call S naught, is the original thing phi 0 of L, which is exactly the same form as what I had with phi replaced by phi L, right, because the other term was just out there, which I'll take care of that. And then a log of plus a constant which actually turns out to be log of the partition function of the short width. What does this come from? It comes from taking the logarithm of this thing. So this thing I write as d phi s e to the minus s0 plus s0 plus s interaction, but s0 of the whole field is s0 of phi L plus s0 of phi s. So this thing becomes e to the minus s0 of phi L, and then there is an interaction S0 of phi s plus S interaction, okay, and so this entire object is S0 of phi L times expectation value of minus S interaction, or rather the average value of minus some interaction multiplied by the partition function of phi S, which is without anything, any of the interactions in it. So this is the partition function with zero coupling. So this is basically the definition. The definition of e to the minus S int is integral phi S e to the minus S0 divided by, and this is the part which became like that, okay, and you take the log of that, you get a formula like this. I think in some literature it's called cumulant expansion. Okay. Okay, no, not yet. This is just something. I haven't done the cumulant expansions. Okay, so let's expand this thing. So I'll take, I assume that you know all this. I'll take this expression. Now this is some constant. So I'm just going to ignore this. This constant doesn't depend any of the any of the couplings of the theory. Just forget about this thing. Okay. So I want to now write an expression for the log of exponential of minus S interaction is given by where does this come from? This comes from the following. Okay, so let's suppose I want to calculate phi S plus S interaction. This is the same thing. Square plus da da da. Okay, so just expanding just e to the minus S interaction. Why could we do such an expansion? Because S interaction had a parameter u. We are assuming that the parameter u is small. Okay, but then this has got to be divided by the whole thing without the test thing. So what that thing does is, so this I'll write as, the first term is just d phi s e to the minus s naught of phi s. The second term is just given by expectation value of S interaction times the partition function, and this thing is given by expectation value of interaction square times the partition function. And then if you do it carefully, you will also see that this term also comes because by the subtraction of the denominator. Okay. So now I want to calculate this term by term. So this is the one I want to calculate. This calculation is very non-trivial. Action is given by K1 to dk4 times 4D. This thing, this bracket means it is calculated in the theory with u equal to 0. Right? That's the way we are doing this expansion. This is a perturbation expansion. Each of the phi I should write at phi L plus phi S. Okay? So let's write this thing out. Some product of dki, and there is a delta function k1 plus k2 plus k3 plus k4. So if I write that thing out, what you will get, there was a factor, so I'll write one factor outside, outside, and then there is a u, which came because I just brought down 1 power of S interaction. As you can see, this is very complicated. Both evaluated at K1, evaluated at K2, and so on and so forth. Okay? So this thing, I'll just symbolically write it like that. So symbolically writing, I'll explain what I mean by this. So this you can, after you keep track of all the factors, you can write this thing as 6 times u, and this is a symbolic way of writing. I'll tell you what that thing is. Either so to the power 4, right? So there is 4, 4, 3, and then okay. What does this thing mean? A term like this means, really speaking, dk1 to dk2, phi s k1, phi s k2, phi s k3, phi L k4, delta function of k1 plus k2 plus k3 plus k4. And similarly for all the firms, I would go mad if I had written down all this thing in gory detail, so I just used a shorthand notation. If I look at this term, so what do I want to get out of this at the end of the day? This is what I want to calculate. So this term had k square plus r phi L, okay, and so that was the original thing, and this is the thing we are calculating. Now I'm going to take the log of this and then calculate that object, and this was a constant. So out of this, if I were to integrate out phi s, I would be left with something which depends only on phi L, right? And let's see what kind of dependence on phi L would it be. There could be a term which is linear in phi L, okay? There could be a term which is cubic in phi L, a term which is quadratic in phi L, and a term which is quartic in phi L, and a constant, okay? Since you, okay, so let's calculate one by one. I mean, we'll show that there is only one non-trivial calculation in out of these 4 terms. The rest of it, in fact, vanish. Yes, e to the k square plus r phi s, and then phi s k1, phi s k2, phi s k3, and then there was a phi l k4 which I'll actually write outside. The reason I wrote it outside is because it's not one of the integration variables. Anybody tell me what is this integral? Yeah? Why is it 0? Good, you got it, because just by symmetry of phi s going to minus phi s, this has to be 0. So that's gone. Same logic, this is gone. This is pretty much alive, and that's pretty much alive. Okay? This one with all the 4 phi s's is going to give you some number. It would not tell you anything. There is no phi L dependence. We are out to look for a phi L dependence on it, because eventually we are going to recast the theory as an action in terms of phi L and read off those coefficients. So we are not interested in that term. So the only thing to calculate is this term. Okay. So let me introduce a notation for calculating these things like this. You represent a line. This corresponds to phi L. I mean, just each phi L, you just draw a line like that. Okay? And then there is a line, a single line, which I call phi S. Symbolically, this thing is then represented by this 2 phi L's and 2 phi L's. So something like this. This term is represented like this. But when you go ahead and evaluate this term, everything is symbolic. So this is phi s of k, phi s of minus k. So phi L k1, phi L k2, and this write phi s k3 and phi s k4 with delta function of k1 plus k2 plus k3 plus k4. Okay. So this is the 2-point correlation function of your theory. You know how to calculate that? So that is phi L k1, phi L k2 and this thing is 1 upon k3 square plus r, delta function k3 plus k4, delta function of k1 plus k2 plus k3 plus k4, and then there are 4 integrals. So 4 integrals are outside. There are 4 integrals. Look what has happened. What has happened is what is called a contraction in field theory. What has happened is that each of these lines came with some momenta from this picture. This is k1 and that's k2, and this is k3 and that is k4, and you have to give some directions to each of them. So I take the attitude I give the direction always away from that vertex. Evaluating this 2-point function gave rise to a delta function which sets k3 equal to minus k4. So what I should do is to close this loop and reverse the arrow here. This is a symbolic way of writing that you have contracted these two things. The official name is contraction. There were 4 integrals to begin with. I have 2 delta functions. So at the end of the day, I should be left with 2 integrals. I can use the 2 delta functions to solve for 2 of the integrals. So let's do that. I'll just write down the final answer here. With all the factors, everything, it turns out that S interaction, that's what we are calculating, is 3 by 2 U. I'll take, see, K3 plus K4 is 0, and then K1 plus K2 plus K3 plus K4 is 0. Therefore, K1 plus K2 also has to be 0. So I call one of them K1, and this is phi L K1 phi L minus K1, and then there is an integral over K3 and R plus K3 square. This is a d-dimensional integral, R plus K3 square. This is the remaining integral. I have used K3 equal to minus K4 to get rid of the K4 integral, and you are only left with a very simple integral which looks like this. Okay, so what do I do with this integral? What is the range of integration of K3? K3 was a momentum of one of the short modes, right? So K3 lies between lambda upon b and lambda. So this thing, lambda to lambda upon b. Therefore, you can actually do this integral. It's not a big deal to do this integral. I'll not do it for any arbitrary b, but this integral is trivial to do for the case of our interest, is to take b when b is very close to 1. When b is very close to 1, the interval of integral is very small, right? And what is this, somebody's theorem in calculus which tells you I can just evaluate it by the interval times the integrand at the midpoint or something like that, right? What is it called? Mean value theorem or something. There's some name to it. Basically, it tells you that when epsilon goes as that's what I, okay, that's how you define an integral as a limit of a sum. So this integral can be very easily done. So let me do this integral. So this thing just becomes 3 by 2 u this 3, the d-dimensional integral over, since it's an integration variable, I might as well just call k, remove that 3 from it. This d-dimensional integral can be written, the measure can be written in polar coordinates as d minus 1 times, this is the volume element on d minus 1 dimensional sphere. This is the same thing as writing dx1, dx2, dx3 as dr r square sine theta d theta d phi. This is we call something d omega 2. Okay, same kind of thing. But this thing is just k square. There's a magnitude of k square. Nothing depends on the angle. So I can bring out the volume of a d minus 1 dimensional unit sphere, and this there was a 1 upon 2 pi to the power d, 2 pi to the power d and an integral of dk, k to the power d minus 1 r plus k square. K runs from lambda upon b to lambda. And again, by that theorem, this is 3 by 2 u. Lambda square and then and there are d objects, so this lambda raised to the power d, and then there should be some constant. This lambda raised to the power d just comes by dimension counting, because you're doing the, all I'm doing is I should do it one little more step once and for all. So by that theorem, this should be lambda raised to the power d minus 1, and then the interval lambda times 1 minus b. This lambda to the d minus 1 combines with lambda to give lambda to the power d. So at the end of the day, this is 3 by 2 and what was the answer? I'll call this some whatever constant and lump it into, I'll call it kd, lambda to the power d. Kd contains pi, this thing, that thing, and all that. But what is important is this factor r by lambda square, and I'll call this, and b is small, times 1 minus 1 upon b. b is close to 1. Can you see this? Okay. What does this mean? What have we done? We are interested in just calculating this object, right? Log of exponential of this, a log of exponential of this was expectation value of s int, and we just calculated the first term in this expansion, right? So up to order u, we get an answer from there. S effective is, I'll write down everything in gory detail now. S0 of phi L was an integral this was a half phi L of k, phi L of minus k. This was S0, and then there was minus of log is just s int, and then plus 3 by 2 u. I'll call this integral also dk, minus k, and times plus order u squared. So once you understand this, I think you will understand the whole works of how this thing works. Look at this now. This is the effective action of the long wavelength modes. This is what I mean by the low energy theory, right? What has happened in this effective action is that this coefficient r, which was the constant term with quadratic in phi L, receives a correction, right? So after one step of integrating out the high momentum modes, I now get a recursion relation which looks like R naught prime is equal to R naught plus just 1 second. 3u kd lambda to the d r plus lambda square, and then 1 by 1 upon b. this whole procedure is justified when B is close to 1, right. So let me write B as 1 plus delta L. Then 1 minus 1 upon B is basically delta L plus delta L whole square plus order. So I replace this by delta L. This is the value of, so now comes the next step. So I didn't write, so let me write first R. It's not R, no. This is R. Okay. The next step in my process, if you remember my discussion of this Gaussian fixed point, was to define dimensionless variables. R is not dimensionless, it has dimension of mass square. So let me define R naught as R by lambda square. So that gives you R naught prime is R naught plus 3u lambda to the power d minus 2, because I have divided by 2, R plus lambda square times delta L. Okay. But, so that means what I get a relationship is, just 1 second, good. And if you remember how we rescale the fields, that I define phi L of k. So I should tell you this integral lies between lambda upon b and 0. Actually, before that I'll rescale the momenta to q equal to b times k. So the magnitude of q lies between lambda and 0. Remember, we have to bring it to a form which looks exactly like its original form, right? So that's why we have to rescale the momenta, and then you rescale the fields by writing phi L of k as b raised to the power 1 plus d upon 2, and then I call phi L of q, or maybe psi L of q. And then I write these two terms. After I do these rescalings, then what you find is the term becomes, so do this together with that, and eventually you get a recursion relation which looks like R at L plus delta L. What I mean by L plus delta L is L was like the log of lambda, and delta L is a log of lambda by b, because that's what that's. So L was roughly like log of lambda, and delta L was 1 upon 1 of times times lambda. So that's log of that, log of L plus delta L is log of lambda upon b. This thing becomes R naught of L. And if you look at this expression, because of the presence of these two factors, let's work out that a little bit. So let me just erase this and you'll work out from that point. So we have that. So if I write the term, it is R plus 3u k d lambda to the d, R plus lambda square, and that is delta L, which is multiplied ddk by whatever, phi L of k, phi L of minus k. K going to q brings in a factor, which is b raised to the power 2 plus d. sorry, which is just b raised to the power k is q minus b, so b d ddq r plus 3u kd lambda to the d r plus lambda square delta L. Phi L I now write in terms of this thing, d by 2 psi L of q psi L of minus q. So these various factors of d and this thing comes down to become d square b dq minus q. So I'll just, and recall b was 1 plus delta L and I'm expanding in delta L. So this thing gives 1 plus 2 delta L and that object gives you R plus 3u R plus lambda square. Lambda is very large, so in that limit, so what I'm going to do, so therefore R naught, the new R naught is the old R naught times this plus 2 delta L, this is also multiplied by delta L, and now you see what happens is divided by R naught is lambda square divided by that. So now you can see so lambda square R naught is given by that. So that gives you R naught is prime is R naught plus 2 R naught plus 3u. I'll write this down again. This is something which you have to do by yourself, because otherwise there's no way you can convince yourself. So I'll write down the whole relationship now. The dimensionless mass parameter R naught at a scale L plus delta L is R naught of L plus 2 R naught plus 3u d minus 4. But I can times that. This 2 R naught just comes from this term. The whole thing, yeah, yeah. This has also a delta F. You're right. And I can just ignore that because you are looking at scales which are much lower than the cutoff scale. So lambda I have to effectively take into infinity. And then you notice the nice thing has emerged that the combination of u and lambda came in the combination of u times lambda raised to the power d minus 4. And if you recall by dimensionless counting, this is precisely the combination that makes u dimensionless, namely the dimensionless coupling is given by u naught is u raised to the power d minus 4, and therefore you get R naught L plus delta L. No, actually I'm not going to, why did I cut this off? I'll keep R naught. To a next order I can ignore that, but I think this is R by lambda square, but that itself is R naught, so I'll just keep this R naught, whole thing by delta L. Long calculation. If I do the next calculation, you're going to die. The next calculation is order u square. But let me tell you how to do that calculation. It's actually lots of 72 terms in principle which are present. But once you know the physics, then you don't need to all that. And once you know the physics and the technique of Mr. Feynman, it's not so hard. This entire thing came from a diagram which was represented by this. That was the only thing that came up to order U. Okay? If you remember, that term which was U times phi 4 became U times phi L 4, and then without coefficients, I just forget about coefficients. So what this means, that if I represent a phi L by a double line and phi S by a single line, these corresponds to vortices which look like this. That's phi L to the 4th. There is a thing which like this, phi S to the 4th. There is a thing which has two of these, that's phi L square, phi S square. Oh, terrible. That is phi L cube phi S, and that is phi S cube phi. Okay. Calculating things to order U meant that I look at whatever number of these double lines outside hanging like that, and I can only use one of these vertices, and whenever I see this single line, I have to join them somehow. And every time I join them, I get a propagator, which is 1 upon k square plus r. Those are in summary the Feynman rules. So when I go to the fourth order, to the order U square, then you have to ask what kind of, so the rule is that you take these things, take two of these, join any way you like, so that there are no hanging single lines. Everything which should hang outside should be double lines. For example, there could be a term with two double lines and one vertex. I took this. I take this and join it with that. I have to join, right? So I join like this and join like that. There could be a term and you might think that these correspond to further terms which are of the order of phi L square, right? Because there are two phi L's hanging outside. It doesn't. The reason it doesn't is that when I wrote that expression, there was an expectation value of S int square minus S expectation of S x int whole square, and these are all contained in there. So these we are not interested in. What else can we get? So these are not important for us. So we start with 2. So can I get something with 3 outside? Okay, 1, 2. Each has to have 4. So if I have 3 outside, say, and another one here, and I just put whatever vertices I like in order to be able to join these things. Okay? So can somebody tell me if I can find something, just looking at those pictures. With 2 double lines on one side, right, there is only one thing which has 2 of these, right. With 1 double line outside, there is only one diagram which is 3 of these. and then there is no way to join these things. It just reflects the fact that the theory must have a symmetry of phi going to minus phi. Just by symmetry, this term cannot happen. Okay? You can convince yourself there is nothing else you can write down. How about a term which has four external legs? That means four double lines outside. I have two, and you can see that there is a nice diagram which looks like this. That is there. What kind of term will this contribute to the effective action? A term which has phi L to the power 4, right? But there is no, the original thing, the original phi L to the power 4 in the S which you started out with had a constant coefficient. There is no guarantee that the coefficient which you get here is going to be independent of the external momentum. No guarantee. In fact, it is not. Okay? What else can you get? How about a term with 1, 2, 3, 1, 2, 3, and join like that? You can get that. This will correspond to the power phi L to the 6th. And as you can see, as I keep going to higher and higher orders of U, you will keep generating things which have not only 4th powers of 5 or 6 powers, 8 powers, you will get, and even the coefficients of the 4th power, 6 powers, 8 powers are not constants. They are functions of momentum. Okay? If you calculate this object, so let's do a very quick calculation of that object and see what happens. Delta function k1 to k4, and then there has to be an integral over which comes from the contraction of the short modes. There will be a single integral there, because if I have a momentum here which is k1 prime and k2 prime, right, that and a momentum here which comes k4 prime and k3 prime, there will be a delta function which sets k2 prime equal to minus k4 prime and k1 prime equal to minus k3 prime, right. So you can just erase one of those, but then the overall delta function also tells you that there will be a delta function in each of these vertices. So this k1 prime must be k1 plus k2 minus k2 prime. So using that delta function, what will happen is that there is only an integration over k2 prime which I have called q. Okay? And the rest again you have to do it yourself. This integral just becomes q square plus r, and then q square plus r, where q is k1 plus k2. It's this 1 upon q square plus r is just, so call this q, is this 2-point function. 1 upon q, capital Q minus small q whole square plus r is this 2-point function, and you have joined them together and done the integral. The magnitude of q in this integral lies between lambda upon b to lambda. And this answer explicitly depends on the value of k1 plus k2, which is the same as the value of minus k3 plus k4. So, what in the action which you started out with, it was a constant times phi L to the power 4. Now we get a function of momentum times phi L to the power 4. There's nothing you can do about it. But if there is a function of momentum, phi k1, phi k2, phi k3 and phi of minus k1, minus k2, minus k3, if this function was a constant, so if f is a constant, this would be the Fourier transform would be just integral of dx phi fourth. If the thing is not a constant, I can make a power series expansion in k1 plus k2, and what this would give rise is to terms like phi squared d squared phi, or even d square of phi square d phi whole square, distribute the derivatives between the two phi's and to arbitrary orders. That was also part of the motivation where I introduced this Gaussian model with arbitrary functions of q. And we showed that things which are very, very high powers of moment are generally irrelevant operators. Now, I don't know a priori that is true. You have to check at the end of the calculation that those are in fact irrelevant operators. For the moment, let's just assume that those are irrelevant operators and proceed. I will not do the rest of the calculation, which takes this and extracts from it the new value of u naught, but I'll just write down what the answer is. In fact, I'll write down the answer in terms of the differential change of these dimensionless parameters under a change of scale. I will define dr naught dl as r naught L plus dl minus r naught of L by delta L, and define something called a beta function, which tells you the this minus sign is just by convention. It tells you how r naught changes as the scale changes, as the cutoff changes, and this relationship can be then written as a nice differential equation and similarly you are going to get a differential equation which for the u naught, which I haven't derived, for small values of u, this tells you what would be the couplings, what would couplings become if I change the cutoff infinitesimally. So it's proceeding a little bit towards going to the extreme low energy limit. Okay? If you're really interested, I suggest at least once in your lifetime. This is such a classic calculation in the history of physics that I really suggest you do it. There are very few calculations of this importance in physics. So what do I do with it? What was our aim? Our aim was to calculate, to obtain a description of the low energy physics. And we said that the first step in achieving that aim was to identify fixed points. So what are fixed points? Fixed points are points values of R naught and U naught, so that if you start at that values of R naught and U naught, you just remain there forever, no matter how many RG transformations you do. That means fixed points must be zeros of beta functions. This one obvious fixed point, which is called the Gaussian fixed point. That's given by R naught equal to 0 and U naught equal to 0. But these equations seem to indicate there could be other zeros of the right hand sides. We will now do a self-consistent approximation U naught R naught small and epsilon 4 minus d is small. Okay, U naught R naught small I understand. What the hell do you mean by saying epsilon equal to 4 minus d being small? It doesn't mean anything. It's just a demonstration that a new fixed point exists. Miracle of miracles is that Wilson and Fisher used this to calculate, as we will show, new fixed points and behavior around the new fixed point. And as I indicate last time, the behavior of slight departures from the fixed points tell you the way these couplings flow, and the way the couplings flow determine to you the critical exponents of the theory. So the calculated critical exponents as a function of epsilon, and in fact they went to order epsilon square also. Later people went up to what, epsilon to the power 8 or something like that. And being very bold people, not being afraid of doing something silly, well, intelligent people are often the ones who are not afraid of doing something very silly. So what they said, let's put epsilon equal to 1. So you get an answer for d equal to 3, right? So a small number in which you are doing an expansion, put equal to 1, you get some numbers out. And lo and behold, for some reason which I don't think anybody understands, those numbers are pretty close to the experimental numbers. I am not going to comment anything more about that, because later on we will show the existence of this fixed point in another approximation where such funny things are not done. It's in the large N expansion where you can explicitly demonstrate the existence of this fixed point. So what is this fixed point? So in this approximation you can neglect, since R naught is small, these denominators can be replaced by just basically 1. So the beta of R naught is given by 2 R naught U naught. Beta of U naught is given by epsilon U naught. So this gives you a fixed point R naught star epsilon sorry, this gives you U naught star must be minus 2 R naught by 3 kd, whereas this equation tells you that U naught star also has to be equal to epsilon by 9 kd. So these two equations then tell you U naught star epsilon by 9 kd, R naught star minus epsilon by 6. Now the final thing is as follows. So let us linearize these equations around the two fixed points. So around the Gaussian fixed point, u naught so that matrix which I wrote down, so this I can write down ddl of r naught u naught has a matrix 2, 3 kd and then epsilon and 0 and epsilon acting on r naught and u naught. So what am I supposed to do? I am supposed to take this matrix, diagonalize it, so that in the new eigenbasis I will have new objects, a linear transformation with r naught and u naught to say r naught tilde and u naught tilde, which has the property that d r naught tilde dl is one of the eigenvalues and d u naught tilde by dl is the other eigenvalue, and you can easily check that those eigenvalues are 2 and epsilon. Because of the 0 here, nothing happens. And the eigenvectors are 1, 0 and 3 kd 2 minus epsilon by 3 kd. So what this means that in that diagram which had r naught and u naught, this was the fixed point and the eigen directions was that and that. This was this eigenvector and that one is that eigenvector. Okay. Now I have to do the same thing around the Wilson-Fisher fixed point. Both these coefficients are positive, which tells you both of them are relevant operators if epsilon is greater than 0. Okay.